Hello everyone, my name is Andong. I was previously a master's student at the Technical University of Munich, and this work was done during my time at Mercedes-Benz. Today I'm very happy to present our work, Unsupervised Domain Adaptive Object Detection with Class Label Shift Weighted Local Features. First, I would motivate why our method is important, and then present some related work in this research area, and then address the problem that we are trying to tackle. After this part, we will present formally our approach to address the problem. In the end, we also demonstrate our experimental result as well as the conclusion. Nowadays, the recent advances in deep learning largely depend on the large-scale datasets such as Cityscapes, Kitty, Coco, or Pascal. However, what if data is difficult to obtain or annotations are expensive? For example, if we train a model in the source domain in normal weather and then directly test the model in the adverse weather, the performance is only around 20.3 MAP. If we, however, train our model directly in the adverse weather, which is the target domain, the performance can be significantly increased to 14.3 MAP. As you could see, there is a huge performance difference even between very similar datasets. If we want to easily transfer a model between two different domains, we typically assume that the features are independent and identically distributed. However, such assumption typically does not hold. Therefore, we need the technique of the unsupervised domain adaptation to alleviate the performance drop due to the distribution shift. Before digging into the object detection task, I would like to take the image classification task as an example. Assume that we have two images, one from the source domain and one from the target domain. And both images are fed into a feature extractor. Typically, we will have two different feature maps extracted from two different images after the input goes through the same feature extractor. And then, based on this feature map, a classifier tries to tell whether the current image is a horse, a car, a tree, or a boat. Meanwhile, a discriminator is used to discriminate whether the current image is from the source or the target domain. During this process, the adversarial training is applied to achieve the marginal feature distribution alignment between the source and the target domain. If, in the end, the discriminator has no idea whether the current image is from the source or the target domain, because the feature extractor during the optimization is trying to confuse the discriminator. In this case, if the discriminator is unable to tell this truth, then, in the end, the feature is aligned, because the feature maps might look very similar, and the discriminator cannot tell the difference anymore. However, it could happen that we actually align the features of two semantically different objects. For example, the features of a horse and the feature of a train, which should not be aligned. Since we have no access to the annotations in the target domain, this scenario could always happen. In this case, the feature is misaligned, but we can still try to address this problem in the dataset level. In this figure, Different color indicates a different class, and every block indicates one image. As you could see, the number of images belonging to the yellow class is different in the source and the target domain. This is the same case as for the blue, the green, and the red classes. Therefore, there is a mismatch between the class distribution in the source and the target domain. Since we have no access to the annotations in the target domain, we can only try to estimate such distribution. After estimating such distribution in the target domain, we can try to reweight the features of different classes in the source domain. For example, the yellow class is less important in the source domain and more important in the target domain. Therefore, we can try to double the weight on the features belonging to the yellow class. For example, we double it, and then we can also decrease the weight assigned to the features belonging to, for example, the red class. Then we can use the weighted features to achieve the marginal feature distribution alignment with that of the target domain. A prior work offers some theoretical analysis saying that when such estimation is perfect, there is a performance guarantee. Now let's come back to object detection. Existing methods developed for image classification can't be directly used, mainly because that one block indicates one image, but in object detection, every image could have multiple objects. For example, in this image, in the left image, there is a horse and a person simultaneously in the same image. Second, the red box in this figure is the receptive field of the corresponding feature pixel in the feature map. And these feature pixels simultaneously indicate multiple objects, including a horse and the person. Third, the object scales are different across classes and images. For example, the size of a horse is different from the size of a person, and also the size of the horse in the left image is different from the size of the horse in the right image. Therefore, the feature reweighting mechanism can't simply be calculated by the number of images. Because in image classification, the contribution of different features belonging to different class is directly coupled with the number of images belonging to each class, while in object detection, this is not the case. So far, no method has approached the label shift adaptation problem in unsupervised domain adaptive object detection. To handle this problem, we propose to first decompose the feature maps by assigning a unique label for each feature pixel in the feature map. The feature map is in the bottom right part of this figure. Also, we try to do a pixel level reweighting. How is this actually achieved? The red boxes in this figure are the receptive fields of its corresponding feature pixels in the feature map. For example, for the left red box, that's the receptive field of a certain pixel in the feature map, and it simultaneously overlaps with the bounding box of a person and the bounding box of a horse. However, it has a larger overlap with the horse. Therefore, we assume that more information of the horse is represented in that feature pixel. Therefore, we assign the corresponding feature pixel in the feature map the label of the horse. For the middle red box, we assign the label of the person because that receptive field completely is completely overlapped with a bounding box of the persons. and for the right red box is completely in the background. Therefore, we can assign the label of the background to its corresponding positions in the feature map. After applying this method, we can again try to use a similar method to reweight the source features. However, this time we reweight different areas of the source feature maps. And now every block in this right figure indicates one feature pixel instead of one image. So how to actually estimate the distribution of the target domain? We try to use the inverse bounding boxes with confidence larger than 0.7 and then periodically update the estimation while inference. Where does the idea work? In the experiments, we pick two baseline methods. One is called SW and the second one is called HTCN. Both baseline methods ignore the problem of the cross-domain class distribution shift in the object detection task. For the datasets, we choose three pairs of datasets. The first dataset tries to adapt the model from a real dataset to a synthetic dataset. The second pair of datasets tries to adapt the model from a synthetic dataset to a real dataset from Synscapes to Cityscapes. And the third pair tries to adapt the model from a synthetic dataset also to a real dataset. The difference between the second and the third pair of datasets is that in the second pair of datasets, the only common class between the source and the target domain is the car, and therefore the performance is evaluated only in the class car. However, in the third pair of datasets, there are more common classes, and therefore the performance is evaluated in more classes. In the first pair of datasets, we could see applying our method to the first and the second baseline, we achieved some performance improvement. In the second pair of datasets, since no existing public dataset pairs are constructed with different degrees of class label shift, and that there is only one class evaluated in this pair of datasets, we can actually try to construct our own datasets and then to achieve different degrees of class label shift across domains. For the source domain, we used the Synscapes consisting of 10,000 images with an overall car ratio around 5%. For the target domain, we try to use 4 different subsets of Cityscapes. These 4 subsets of the Cityscape have different overall car ratios ranging from 16% to 8%. These different overall car ratios are achieved by sampling different number of images from 2 parts of the datasets. The 1 parts are the images of the dataset which have overall less than 10% of the car pixels of feature pixels belonging to the car, and the rest part are the images which have more than 10% of the feature pixels belonging to the car. By controlling the number of the images sampled in both datasets, in both parts of the dataset, we achieve the different overall car ratios in 4 subsets of Cityscapes. These 5 figures shows the comparison of the bounding box sizes distribution. From left to right, the bounding box sizes increases, and the units are the pixels. As you can see, the major difference between the different subsets of the Cityscapes are caused by the very small and the number of the very large bounding boxes, as indicated by these red rectangles. In the experiments, we compare our method based on the baseline SHTCN by deactivating its transferability maps and feature vector concatenation design. In the later ablation study, we will show the interaction between these two designs and our design. Compare the blue line and the red curve. In this figure, we can see that our method can systematically improve the baseline SHTCN across different degrees of class label shift. Surprisingly, our methods can even directly outperform the full version of the HTCN. Compare the blue line and the brown line. Interestingly, we can see that from the left to the right, the performance is generally increasing. The possible reason is that in the subset with larger ratio, there are generally more large bounding boxes. Therefore, in all methods, the performance tends to increase because larger bounding boxes are generally easier to detect. In the third pair of datasets, we adapt the model from Synscapes to Cityscapes. The first line in this table shows that we trained our model only in the source domain Synscapes and directly tested in the target domain Cityscapes. It achieves 25.2. We do this because this is not a standard benchmark dataset in this research area. And then we try to apply the baseline method HTCN, which achieves only 23.9. We found that it might be due to the fact that the source domain Synscapes and the target domain Cityscapes already look very similar. Therefore, the advantage brought by the marginal feature alignment might not be that big, and the disadvantage brought by it during the feature misalignment might be even larger, and therefore the adversarial training-based marginal feature alignment in this case even bring negative effect on the overall performance. However, after additionally applying our method on top of it, we can still improve the baseline HTCN method for 1.3 MAP. Therefore, our methods should always be applied no matter whether the appearance difference is large or small. In the ablation study, unless otherwise indicated, all experiments use a fixed hyperparameters unless that parameter is the parameter specifically studied. First, we try to see the interactions between two designs in the baseline HTCN and our design. By deactivating both methods, the performance is only 39.6. Compare the first line and the third line. Additionally, using our method could directly improve the performance significantly. Also, compare the second line and the fourth line. Our method can still improve the full version of the HTCN. In this experiment, we try to study the effect of the confidence threshold that we use to pick the predicted bounding boxes in the target domain. It could be easily seen that it's not very good to set the confidence threshold to be too high. It might be because setting the confidence threshold to be too high lets the model ignore too many bounding boxes during the training. For the update interval that we use to periodically update the reweighting factors, we found that it's always better to use a more recent estimation, which means a more frequent update is always better. The future work includes to investigate other types of the label shift, including the size of bounding boxes and the relative positions of the objects. Both could be expressed by a histogram using our proposed decomposition feature map decomposition, and then see how often one feature pixel simultaneously indicates multiple objects. To conclude, we propose an intuitive mechanism to decompose the source feature map and we use an iterative approach to estimate, update, and utilize the pixel-level class label shift. This method could empirically improve the performance by alleviating the cross-domain class label shift problem. To the best of our knowledge, we are the first to propose the mechanism to correct class label shift for object detection tasks in pixel level. Thank you for your attention.